Hi everyone, this is Kai. What I'd like to do in this video is to show you two more examples for the usage of the fodMC. In one of them I show you how you introduce multiple bond FODs. And the other example is used to show you how an incorrect input looks like and how you can analyze the output of the fodMC to see that. And of course, in addition, I guide you through how you fix such an incorrect guess. So once more, we go into the examples folder and into our system file. And I want to use the second example, so I'm going to copy it up top. The input structure I explained in the last video. The only difference is here is now that we have an additional keyword called fix1s, which places the 1s FODs at the nuclear positions, in this case of these two carbon atoms. And in addition, we now have a bond pattern that we specify explicitly, which is explained as follows. In the first parentheses, we have the atomic indices, in this case 1 and 2. So this describes a bond between atom 1 and atom 2. And after the minus sign, in parentheses, we have the bond pattern, which is 2 up and 2 down FODs. So this is the double bond that we need in C2H4. And if we execute the code, we can again analyze the bond information in lone FODs. We see the bond pattern of 2-2 between the carbon atoms. All the oxygen atoms have single bonds to the carbon atoms. We have no charge, no spin, no dipole. So all of that seems totally fine. And upon visualization, we see in gray the carbon atoms and in white the hydrogen atoms. In between each hydrogen and each carbon, we have one pair of up and down FODs along the bond axis. So these are our single bonds. And here, in addition, we have two pairs of up and down FODs in between the carbon atoms, oriented perpendicular to the bond axis. So this describes our double bond. So this is a proper guess for C2H4. And now I'd like to go to an example where you got to be more careful. So the example is COH2, where we would expect a double bond between the carbon and the oxygen atom. But as you can see, I do not specify that at all. So I blindly use the fodMC as a black box method. And if I run the code, I see that I have a problem. First of all, the bond pattern between carbon and oxygen is 1-1, which is not what we wanted. Furthermore, we have a single unpaired up FOD in the lone region of the carbon atom. So this carbon atom is spin polarized. Similarly, for the oxygen, we have a bond pattern of 1-1 and more up than down FODs in the lone region. So our oxygen atom is spin polarized, which leads inevitably to a total spin of our system of 2, which is simply wrong. And visualizing this guess, we see a similar story. The bonds between hydrogen and carbon, these are fine, these are single bonds. But we only have a single bond between carbon and oxygen. We see that we have 3 up and only 2 down FODs in the lone region of oxygen. And furthermore, we have this single unpaired lone FOD at the carbon side. So this is not what we wanted at all. And in order to fix it, we have to introduce a bond pattern. And this bond pattern is now the same as in C2H4. We say that between atom 1 and atom 2, we have a bond pattern of 2 up and 2 down FODs, so a double bond. And now running the code, we see a much nicer pattern. So the bond pattern between carbon and oxygen is 2-2. We don't introduce any unpaired lone FODs. Our total spin is 0. Our total charge is 0. And if we now analyze this gas visually, we see, of course, the carbon-hydrogen bonds are fine, but we have 2 pairs of up and down FODs in the lone region of oxygen. We have an additional 2 pairs of up and down FODs in the bond region between carbon and oxygen. So these are our bond FODs. And this picture makes much more sense. So the entire output of the fodMC can tell you whether the gas that you generated is right or not, and you should always make sure to analyze the output properly before using these gases in any calculations. To summarize, the fodMC is not a black box method, should be used with care, but if you use it with care, you can initialize any bond pattern that you want and analyze that later on. That's it for this video. Thank you very much.